So we welcome Thomas Strobl, and the title is already on the screen, Arborescent Koszul-Tate resolution and BFV for singular coisotropic reductions, sorry.
Okay, welcome. Oops. So this is mostly collaboration with Alexander Hancharuk and in part also with Camille. And it is about singular coisotropic reductions. So in many situations in mathematics, but equally well in physics, there are always regularity conditions imposed to perform symplectic or coisotropic reduction for good reasons. And if you drop this, the question is how to proceed, and physics actually guides us away and says there is another way of dealing with the system, and that is the Bartholin-Wiekowiski, or in the Hamiltonian formulation, the Bartholin-Fradkin-Wiekowiski formalism, where you extend your space and recast everything as a cohomological problem. And this was attempted also by other people already before, and we are happy to say that we kind of found a more or less complete solution to the problem under very mild conditions. So the plan of the talk is as follows. I first recall some facts, simple facts about symplectic reduction or coisotropic reduction, and about the BFV formalism, what the data are. And then the two parts of the title. So first, the Koszul-Tate resolution, which is just a resolution of an ideal inside a ring, or of the quotient, better to say, by some differential graded algebra, which at the same time is symmetric algebra over a graded module, so that you can think of it as polynomial in ghosts, or anti-ghosts actually. And the main test here is that the cohomology at degree 0 is this quotient, and otherwise there's no cohomology. And then in the second step, we add the Poisson bracket to the game. We say that this is a coisotropic Poisson subalgebra, and we construct the BFV data. This again gives a DGA, another one, but of the same sort, but in a bigger space. There are also ghosts and anti-ghosts. And here the main criterion is that the zero cohomology describes the reduced Poisson algebra. Other cohomologies, by the way, are not supposed to vanish. So let me start now with the introduction. So suppose you have a symplectic manifold and a coisotropic submanifold C, which means that if you look at the vanishing ideal of this submanifold, then it forms a Poisson subalgebra. So this is, in Dirac's terminology, the first-class constraints. And then if you look at the flows of vector fields generated by elements in this vanishing ideal, then this forms an integrable distribution on this constraint surface C. And if everything is smooth, you can look at the leaf space. So there's this projection down here, and you get another symplectic manifold, the reduced symplectic manifold R with its symplectic form omega R. If you want to go to the singular setting, we need to reformulate everything algebraically, and so I do already here. The functions on this reduced space are the same thing as the normaliser of this vanishing ideal in the Poisson sense, which are in the Dirac terminology, the Dirac observables modulo this ideal, so which is like essentially functions on C. So this is the classical setting, and an example of this setting is when we are given symmetries. So suppose you have a group action on a symplectic manifold with an equivalent moment map, that is a map from this symplectic Poisson manifold to the dual of a Lie algebra, and it's a Poisson map. It's called the moment map, and then one looks at the pre-image of 0 under this map, which gives the constraint surface, and the quotient by the group action, which sometimes is then also written with a double quotient because it has two steps, the restriction and the quotient. And in generically, this is not smooth. To give you a very simple example where it is not, look at the case of rotations on R3. Yeah, I thought the same. Okay. So rotations on R3, for any group action, there's a canonical lift to the cotangent bundle over that manifold. So we are now in phase space over R3. We have coordinates x and p vector. And the moment map gives a map to SO3 star. And it consists of precisely this combination, SO3 stars and R3. We come from R6 and R3. This map from R6 with x and p's to R3 is given by L vector, which is the angular momentum, which is the vector product of x with p. Here I wrote it also in the components. And the constraint surface being the pre-image of this map mu of 0 is putting all this angular momentum equal to 0. If you reflect a little bit, you see that this is not a submanifold. There are problems if either x or p are 0, and also the quotient is not smooth. Okay, so this is like a very natural example where you run into a singular situation, and this will be our guiding example in all what follows. So what do we do in the singular setting? So we look at what we call with Hardy and Ahari I-Poisson manifolds. So in the simplest setting, this is just a Poisson manifold together with an appropriate ideal. Here are some of the conditions. And an element, the Hamiltonian in the normalizer. Here I recall what the normalizer is. So these are all the functions on the Poisson manifold which the Hamiltonian vector fields of which leave invariant this ideal. The condition of local finiteness is needed, for example, to ensure that the flow of this Hamiltonian of an element in the normalizer stays inside the ideal, at least when complete, otherwise it's an appropriate notion. And the reduction now is, given these data, you see that actually, while the functions on P modulo I do not form a Poisson subalgebra, with this condition, the elements in the normalizer do. So you can look at this quotient, and it is a Poisson algebra. I call it R for reduced. And also you can look at this function in that quotient. It lives already in n of I, so in the quotient I take the bracket around. That's the reduced Hamiltonian. And that is sort of say what we want to obtain and how we describe the reduction in algebraic terms. And two examples. So the coisotropic reduction mentioned before, this reduced Poisson algebra is just what we had, the functions on the symplectic reduced phase space, and this is the induced Poisson bracket. And in the angular momentum, for example, if you look at in the polynomial setting, so you look at the, instead of the small functions, look at the polynomials on R6, and you look at this ideal generated by the 3 angular momentum in the polynomial setting. The reduced algebra is the symmetric product of the Lie algebra SO to 1, and there's no mistake in the signature here, modulo the quadratic, what is generated by the quadratic ideal. Just to give you some idea, SO to 1 is a 3-dimensional Lie algebra. Its dual is a Poisson algebra. It's a 3-dimensional space, and its symplectic quotient orbits or symplectic orbits are hyperbola, and in particular for the Casimir equal to 0 is the light cone. So we see that in this example, quotienting by this ideal, it means that you restrict to the light cone in R3, which is more or less a two-dimensional submanifold, except at the origin it's not smooth. So this is a reduction in the case of the angular momentum in the polynomial setting. If you do it in a smooth setting, you get just one copy of the two of this light cone. So what is the BFV? We had a little bit in Pavel's talk yesterday, but just to set the stage. So it's a graded manifold with a graded Poisson bracket or Poisson structure, Z graded, not N or not positive or negatively graded. This symplectic structure has degree 0, and it's supposed to live over the original symplectic manifold. So this is some bundle over it. And the additional data is that you have a function on this graded manifold of degree 1, another one of degree 0. The degree 0 one is an extension of the Hamiltonian you are given. So these dots, dots mean contributions, so this H is the pullback from here, and then there are elements which are not pullbacks. And the two main conditions for this data are that this is the so-called classical master equation, that Q squares to 0 with itself, and actually in the BFV formulation as a second classical master equation, namely that the extension of the Hamiltonian HBFV should be also QBFV closed. So these are absolutely necessary conditions, and then the main goal of the whole procedure is that the cohomology of, so if you take the Hamiltonian vector field of this charge with respect to the induced graded Poisson bracket, the BFV bracket, we get a homological vector field, and its cohomology at degree 0 should be the reduced algebra. And this class, and the cohomology should be isomorphic to this class of the Hamiltonian we discussed before. So that is the classical setting, and that is what we are going to construct. And I show you a strategy that we will pursue. So we are given an I-Poisson algebra. So O is now any commutative associative R algebra in the ring. This is a Poisson algebra. Here I is a finitely generated ideal, and we have this Hamiltonian. And in the first step, the second part of the talk, we construct the first differential graded algebra in the game, which is the Koszul-Tate resolution of the quotient. So it's the first step of the reduction. We go to the constraint surface, but now in the algebraic setting, where it is also possible if this constraint surface is not a submanifold. So here in this setting, we completely forget about the Poisson bracket. This we turn on back in the second part, or third part of the talk, where we obtain a bigger DGA from this data of the BFV extension as explained before, where now I gave up the symplectic. I just wanted the Z-graded Poisson manifold, which extends in degree 0 the original Poisson algebra I'm given, not manifold algebra. And so here are these two DGAs. So I follow again Pavel with his idea of relating to the title of the conference. And the main physics is to check that really this holds true. So that is the input from physics. That is what we want. The quotient is that what describes the physical world. Okay, so let us go now to this second part where we construct, we forget the Poisson bracket, we have just a ring with an finitely generated ideal inside, and we need one assumption for the whole thing to work, namely that we have already a module resolution of this ideal inside the ring O. So, and it's a free resolution. So this is a complex, and everywhere the cohomology is 0, except here you see that the image of this degree 1 module is supposed to be the ideal, and O is mapped to 0. So the cohomology here is just the quotient of O over I. And that's, we assume that we have given this modular resolution. Actually, this assumption is relatively weak. If you, for example, have, one second, if you have a Noetherian ring, you always get this for free. Or if you have, say, polynomials like in the angular momentum, always these resolutions exist with finite capital N.
No.
Okay?
Almost never.
Okay, it depends on.
Quillen proved that if it's not LCI in the algebraic setting, if it's not LCI, it will go.
Okay, it depends on what you consider generic. Yeah, okay, very good. But okay, but in
That's like an unrealistic hypothesis.
okay.
Are you dependent on that hypothesis?
We are talking about modular resolution.
Or modular resolution? Are you not taking, this isn't the tape.
No, that is a starting point.
I'm sorry.
Okay.
Okay.
Okay, the other one we are going to construct, that's the main point.
Yeah, okay, sorry.
Okay, so given this modular resolution, and at least in settings which in the physical applications would be very natural, like the polynomial generators of the ideal, this always exists by Hilbert's theorem. And given this, let me illustrate it first for the angular momentum. So here, the ring of functions is the functions on T star R3. We can take either these or the polynomials, and we take the ideal generated by the three angular momenta. So there are three generators, so that here at degree 1 we will have a rank 3 O module. We call the three generators of M1, Pi1, Pi2, and Pi3. The rank is 3 because we have 3 generators, and we impose that this differential just acting on these generators pi a of degree 1 just produces the generators of this ideal. But these generators have redundancy relations among them. So you see this is the vector product of x with p. So if I take the inner product either with x or with p, I get automatically 0. So I have two such relations, which imposes that this should have rank 2. So for each of these relations, I introduce a generator of degree 2. I say that the differential of, say for example, the first of these is xa pi a, and you see it's constructed in such a way that if I now take this partial square on pi, then I just reproduce 0 by this relation. And it turns out that this is a resolution. So we have only two entries. This capital N in the length of the modular resolution is 2, and the ranks are 3 and 2 in this case. Okay, any questions here? Okay, now there is a standard procedure in principle to construct this Koszul-Tate resolution. I just want to illustrate first what is the problem and why is it not satisfactory in the standard setting. So suppose we have given this modular resolution M1, M2, so we say that so epsilon should be this Koszul-Tate resolution. I put KT here. So in the first 2 degree, it's just M1 and M2, and this differential is just the original differential. And now, however, we want the differential graded symmetric algebra, so an algebra of polynomials of these ghosts, how they are called in physics, so that at degree 2, for example, we also have the graded symmetric tensor product of M1. And so here we in general will find new cycles which are not in the image of M3. I will give an example in a second for this angular momentum. So we need to add something here to kill them. And this is an infinite procedure. As you can see, you not only need to calculate all the cohomologies at each level, you need to proceed ad infinitum in general. So this is the procedure. So at degree 3, you have the modular resolution of degree 3. You need to add something here, but then you also have products of degree 1 and degree 2, or triple products of degree 1, and so you will have to add here also a big new bunch to kill the new cycles coming from this extension of the modular resolution. Let us look at an example. So in the example of this angular momentum, we had M1 and M2 was the modular solution. And for example, in here, we can look at this combination. You see there's one linear in these anti-ghosts, or these pies in any case, of this form. And here's something quadratic in the degree 1 ghost. And one can just check that this is closed. So to kill it, we need, and it's not exact in the modular solution, actually there's nothing on degree 3, so it cannot be. So you add something now, and since you have 3 of them, you add 3 new generators, such that its differential gives these cycles. And right, and the problem is that one needs to continue ad infinitum here. And in principle, this procedure, however, would yield you a minimal Koszul-Tate resolution. So you don't get anything too much if at each step you just calculate generators of the cohomology. And the ranks in this case is we had already 3 and 2 at degree 1 and 2. Then here we see in the angular momentum we get 3 at that level. And if one continues calculating, we get 6 at that level. I'm saying this because later we will compare this in our construction. Yes?
In degree 2, you should get 8, because you had M2, which was rank 2, and S2 of M1, which was rank 6.
No, here I'm talking about the generators of epsilon kt.
Oh, the generators?
Yes,
Oh, okay.
of the generators. And then you take S dot of those generators, which is bigger, absolutely. Yeah. So these are the number of ghosts you need at each degree. So as mentioned, the disadvantage is that you need an infinite number of calculations, or in general, so in more or less it's not constructed. So, and that we can resolve in the following construction, which we found with Sasha and Camille. So we will construct such a polynomial algebra of ghosts with a differential, which will be a resolution of this quotient, where these ghosts actually take the role, will be played by decorated planar trees, so in colloquial terms by Christmas trees. And how does this work? So let us first start with looking at all planar trees without decorations. So here tk bracket n describes the planar trees with k vertices and n leaves. For example, this one would have 2 vertices and 4 leaves. And we want that the vertices are at least 3-valent. And for example, we add also with 0 vertices and 1 vertex, the trivial tree, or it just is there, has 1 leaf, and we call this over in the bottom was the root. And if you have 0 vertices and 2 leaves, such a tree doesn't exist, so there's just nothing here. But for example, if you have 2 vertices and 4 leaves, then here are some examples of those trees. Now these are the naked trees as they are. Now we decorate them, so at each of the leaves we put an element of our modular resolutions, so those are the Christmas balls. And this generates a free O module, and we will call the resolution degree the number of vertices plus the sum of the degrees of the leaves. And the generators of this resolution, epsilon, will be these trees, actually the sum of those trees here modulo and symmetrization, which I'm going to explain now. So let's go back to the angular momentum as an example. So we had two modules for the resolution of the module. I put yellow dots for those of M1 for the decoration and blue for those of M2. So these are the colors of the leaf. And for example, if I look at such a tree, it has one vertex and two Christmas balls of degree 1, so this is a degree 3 object. If I now replace one of those balls by a degree 2 one, a degree 4, degree 5, and certainly the more complicated trees. And now what we want to factor out is if, for example, alpha I and beta j are these elements in the module, and we swap them, we want to get a sign and to identify such trees. And more complicated, for example, if here I swap the same, so if this happens inside a tree, it should happen, but also if I swap a subtree here, then this subtree has degree alpha of alpha I of beta j plus 1 because of the vertex, so this is taken into account. So these are now, this epsilon dot are this module of symmetrized decorated planar trees, and we take a forest of them. So we have several such trees, and again we quotient by symmetry in the symmetrized product, and that is our graded algebra. Now we need a differential. And how do we construct a differential? There are actually three contributions to it. The first two are very easy to understand. So the first one of this delta is to just remove a vertex. For example, if I remove this one, I get one tree here and another tree, so I get two trees. So this is in the forest. However, I can also let collide this and this one, which removes one tree, and then I get such a tree with some signs which I suppressed here. So that's the first contribution. It's just acting on the trees, just removing a vertex. Then there's a second contribution, which, with exceptions, which I will mention in a second, just acts with the module differential on the leaves. So with some signs which depend also on the tree below. And this actually is true if the degree of the decorations are bigger than 1. Because you remember, if they are degree 1, then partial acting on it puts you back into the module. And we don't have trees where you place here an element in the module, so such a tree doesn't exist, or it would be like just drop this leaf, it doesn't exist. So we need some other rule for the fact if the degree of the leaves is 1, if one of them is 1. So, but otherwise it has this contribution, and because of this problem, we need a third contribution for it to square to 0. So what did I write here? Yeah, so that would, yeah, that is what we will get. So with this d gamma we can put down, this tree exists. But now because of this change of the rules, this second delta doesn't square to 0. Otherwise it would also square to 0. They would anti-commute these two deltas, and you would have our total deltas. But now we need something else, and actually this something else is not canonically given. And it needs some choices, but these choices are only to be taken up to the degree of the module resolution plus 1. So it's a finite number of choices. And I will illustrate this with the angular momentum, although there are no choices, but still there's an extra contribution. I will show you. So what we need to do is we need to look at all subtrees which have degree smaller or equal to n plus 1. So n in the angular momentum was 2, so we need all trees of degree at most 3. Actually, for the angular momentum, there's only one type of such a tree. Right? There's one vertex and 2 leaves of degree 1. And now we need a map acting on this tree, which maps this tree into a trivial tree with an element in the module of degree 2. And this is constructed as follows. So look at these alpha and beta leaf in here. If I apply delta to it, I end up in M1. and this is a closed element. So because we have a model resolution, it must be the image of this partial of some element in M2, and because here it's even the end already of the sequence, this element is even exact, so unique. So here there's no choice, but in general there will be a choice evidently. And so you need to find this element, and actually this defines here on this module resolution an algebra on the module resolution, which is a DGA, and the product is actually given by this phi. In any case, then the third contribution is whenever this delta 3 hits such a subtree, it replaces the subtree by this trivial one. Yeah. I illustrated, so if in the case when we have more than a longer than resolution 2, then you have an M3 here, and then there is just such a phi living here, but there's an ambiguity by adding some element in the image of partial. So here, at each step, we have a choice, and we need to look at all trees of at most degree capital M plus 1. Okay, but this is a finite number of choices, choosing representative of cohomology classes. And then the main theorem is that now the thus constructed DGA is a resolution of this quotient. So that's the main theorem, and there's one small caveat, namely that it is not a minimal solution. So if we just calculate explicitly in the case of the angular momentum, we find like before 3, 2, 3, but here instead of 6, which we found in the Tate algorithm, which is minimal, we find 7 in this case. So there's a price to pay, but we don't have one. Like this construction is now after these choices we had to make. Now it's canonical. These trees all exist, delta exists, everything's done. And there's one more thing which we can use, namely there's a homotopy starting from that degree. And so this is a very simple thing actually. So it's just, it takes a forest and just puts all the trees into a new tree. So it's because it adds a vertex, it is of degree plus 1, and now it just checks that indeed for a high enough degree, this is a homotopy. Note, by the way, that the whole resolution does not permit the homotopy. So we can prove that in lower degrees for angular momentum there is no homotopy. Just evaluate at 0 and you see it cannot work. But here this is a homotopy in this construction.
But I'm confused. Can we just be careful, because you can't, I mean, there is cohomology all the way, so, but this...
Not in this one.
Oh,
This is a bona fide resolution. So this is a bona fide resolution.
Cohomology of this, but the cohomology, you're calculating what's called the autoequivalent homology of the singularity, and that has arbitrarily high.
Okay.
Sorry, homology, and that has arbitrarily high.
Okay. The theorem is that this is a resolution, so only at degree 0. Only at degree 0 we have homology, or homology I should call it, I think, which is the quotient, and at all other degrees we have...
What I mean is that there are generators all the way.
Sure, yes, yes.
Oh, you're not commutating your... Oh, I'm sorry, I understand.
Mm-hmm.
Okay, good.
So we have this homotopy, and so the advantage over the Tate algorithm is that this is a construction. So, and it needs a finite number of choices. And moreover, it should be very useful for the BFV context. We do have a homotopy at sufficiently high degrees. Now, there are several things one can say in addition about this construction. For example, one thing is that these choices we needed to take, they induce an A infinity algebra on the original module resolution. In the case of angular momentum, this has to be a DGA. And I mentioned it, this map psi or phi, whatever. This was a product which equips this length 2 model resolution with a differential graded algebra. And generally, you get an A infinity algebra at this point. What we don't know if this A infinity algebra alone induces all our construction. At the moment, it seems we need more, but one would conjecture it should be sufficient. Another thing is we can now use this to prove that in many cases, like in the angular momentum, we indeed need an infinite tower of these generators. This can be done by going to a minimal, from each Koszul-Tate resolution, like from ours, we can go to a minimal one in some situations like those of the angular momentum, and in there we can find trees of arbitrary degree. And so we see that it doesn't stop. Okay, now the second part about the BFV formulation for such a theory, which we worked out with Alexander. So the Koszul-Tate gives us this resolution of this quotient, and it corresponds to the restriction to the constraint surface inside the Poisson manifold in the smooth setting. And now we put back the Poisson bracket on O, and we want to get all these data we mentioned before in this BFV data, such that we get a description, a cohomological description of this quotient of the physical or reduced Poisson algebra. And so how to do this? So first of all, for all these trees we have before, we double them. So, and the trees before we actually call anti-ghosts, and their shadows are called ghosts. So I choose them here, and now we look, the graded algebra is just the polynomials in these ghosts and anti-ghosts, so all in all those trees. Certainly at degree 0 we have back the original Poisson algebra, so here. And since we have them doubled, we can, and they have also opposite degrees. So for example here, these are the generators of negative degree. These correspond to these, what we had before, the trees from before. I have them with orange vertices, not vertices, links, and their copies are the same trees but with red edges, and they are in the positive degree, so we can now always pair them in the BFV bracket, which is supposed to be of degree 0. And what we had before is this delta and H acted only on this, and one part of the situation is to extend this to the bigger setting. So to construct the data of this nilpotent charge Q and the extension of the BFV Hamiltonian, let me go back, one uses this degree. So we have a bigrading here. We have a total degree, which is just the sum of the two, but we have here the ghost number and here the anti-ghost number. And since in the anti-ghost number, extending these elements to the total setting, we have no cohomology. We can construct step by step what to search. So the total degree is the ghost number, but not plus the anti-ghost number, but actually one conventionally changes the sign here. So the ghosts, which were on the right, had positive degrees, are called etas, often in the physics literature, and the momenta, which are the original trees we constructed, they have ghost number 0, but they are the anti-ghosts. And now, because of this change of sign, they also have positive degree, but anti-ghost number. And the delta has now degree +1 because it swept the sign in the We sweep the sign in the Koszul-Tate resolution, and H, which had degree +1 before, the homotopy has now degree -1. So now we can, in principle, before we start any calculation, we can decompose any of those charges with respect to this anti-ghost number, which is non-negative, so we have just each element here, and we want to solve now order by order these two classical master equations, but with certainly some boundary conditions, namely one being that, for example, this HBFV should start at anti-ghost number 0 with the original Hamiltonian, and there is some other condition here where this eta delta pi is roughly what it suggests. So eta is the ghosts, pi are these anti-ghost original trees, delta is the thing which acts on those, and we take the anti-ghost number k of it. I illustrated here. So so here we take all trees pi of anti-ghost number k plus 1, we act delta on it. Well, delta had degree +1 now, so I don't know. I hope these degrees are correct. And then we multiply it by a corresponding shadow, and we sum over all these trees of that degree. So that is just a boundary condition to solve here. And that this will be essential in the end of the day to ensure that the cohomology is the right one. And then the theorem we have is that indeed there are such extensions, QBFV and HBFV, so there's a solution to the problem. It's not unique, the solution, but for k bigger than the module resolution degree, we can use the homotopy. So we have only choices up to that degree to take, and then we have recursive formulas of this form for Q as well as for, I dropped the BFV here. For this Q and the HBFV, we have such recursive forms where you see the homotopy in the game. And the main part is that indeed the cohomology of this Batelin-Fratiel-Wieckowicki DGA gives really what we want, the reduced algebra as Poisson algebras. Let me finally, as a final example, come back to the angular momentum. So the original trees we constructed are now the anti-ghosts. I labeled them here again. And the ghosts are the same trees, but just we replace the edges by another color to distinguish them. They are of degree 1, 2, 3. They will be of degree -1, -2, -3. And you see at degree 4, for example, you have this is degree 1, this is degree 2, and this is degree 1, the vertex, so this is degree 4. But you also have such a tree. And then why do we have 7 of them? Let us count together. So here we have 2 choices. Here we have 3 choices, because degree 2 we had rank 2 of the module resolution. Here with rank 3. So this gives 6 trees of that sort. And then because it's completely antisymmetric in those, it's 1 tree of that sort. So here we get 7 trees. It continues like this. There's an index A to label the generators of these decorations. We had 3 in here, and here we had 2, like capital A. And now the BFV charge, for example, you need to make some choices in the first degrees, and the rest now follows by the recursion. So they're, in that sense, complete formulas. Maybe nice to find an explicit construction, but we played around a bit and didn't find like an explicit description of the order k. We just can use this recursion. Just to remind you of the notation, so LA are the angular momenta, and these are the ghosts which correspond to them. So this is the standard term every BFV charge starts with. You have the ghosts times the constraints. And the next term, you see here the structure functions of the constraints, which here form an SO3 Lie algebra. There are two ghosts and one ghost momenta. So this is a very standard BRST contribution, but it's far from sufficient here. We need to add infinitely many more such terms, and also we have an infinite tower of new ghosts. These ghosts which conventionally are here are not sufficient. I rewrite the same formula now with symbols, more mathematical terms if you want. So if I call the ghosts eta in this fashion and pi their momenta or anti-ghosts, then this just such constructed BFV charge has the following form. So here is this usual BRST contribution. Actually, it can be viewed as follows. So there's an action Lie algebroid on R3, and you can view it as a graded manifold. You can go to the cotangent bundle, look at the cotangent lift of this, and you find this charge. However, this charge has not at all the right cohomology. Even if I exclude the origin, it gives you the wrong cohomology. And the reason is that I forgot about relations. So now actually I have two such relations. Another idea we had at some point with Sasha was, instead of taking the Hamiltonian lift of Weintrop's Q manifold for the action Lie algebroid, we'd look at the universal Lie infinity algebroid, which just has length 2 in this case. So it's a Lie 2 algebroid structure on this modular resolution. Actually, that's not true. We look at that and take Hamiltonian lift, but there the relations are only in X and not in P, so this is also not sufficient. It gives the right cohomology if we exclude the origin in X, but if we put it back, we get the wrong thing. And in reality, we need this infinite tower. And for example, if now we want to add a Hamiltonian, so let's take a rotation invariant Hamiltonian, the kinetic term, plus, say, harmonic oscillator with frequency square root of alpha, then the BFV extension, so in the first level, degrees of the anti-ghost number, we need to choose something. And so this is here my choice. So you see one contribution which is coming from here, and the alpha signals that it's a contribution which is needed from here, and all the others we can get from the recursion. But it doesn't stop. And thank you.
So thanks a lot.